Welcome to this screencast in which we cover energy and power signals. In a previous screencast introducing spectral estimation, we saw that in practice we often have a few samples of a random signal available. This means we do not have the full infinite length signal, but a window version of the signal. Thus, we cannot calculate the true autocorrelation function, but an estimate of it. Moreover, in theory, the Fourier transform exists only for signals with finite energy, but most random signals are actually aperiodic power signals. As we shall see, this has important implications in the calculation of the power spectral density. The result is that we can only look for an estimator of the power spectral density given the observed signal. Before we dig into such estimators, let us review the concept of energy and average power of a signal. The total energy of a signal x is given by the square modulus of x over all time instances. Here we focus on discrete time signals, but the definition for continuous time signal is easily obtained by substituting the sum with the integral. The energy is also the total power of a signal. If we want to calculate the average power, we need to first calculate the sum over a period and then take the limit for the period that goes to infinity. Once we have defined the total energy and average power of a signal, we can distinguish between energy and power signals. An energy signal is a signal which has finite energy, while a signal with finite average power is called power signal. Note that for an energy signal, the average power is 0. An example of energy signal is a delta pulse. In the slide, we see a delta pulse with a constant amplitude A. Since this is a continuous time signal, to calculate the energy, we need to integrate from minus infinity to plus infinity the modulus squared of the signal. By definition, the integral of a delta pulse is equal to 1. Thus, the energy of the signal is A squared. Since this value is finite, we can conclude that this is an energy signal. An important property of energy signals is that the Fourier transform exists. Thus, we can rewrite the definition of energy in the frequency domain as shown in the slide. The argument of the integral can thus be reinterpreted as the distribution of the energy over frequencies. In fact, when we integrate over all frequencies, we obtain the total energy. From this, we obtain the so-called direct method to calculate the energy spectral density, also called energy spectral distribution function. As shown in the slide, the direct method consists in taking the modulus squared of the Fourier transform of the signal. Starting from the direct method, we can walk our way through the indirect method. We first rewrite the modulus squared as the product of complex conjugates. Then, we use the definition of Fourier transform to rewrite this in the time domain. By defining a new index for the summation tau equal to n minus L, we can rewrite this in a form which is equivalent to the Fourier transform of the autocorrelation function. This way, we obtain the so-called indirect method to calculate the energy spectral density. It is indirect because it requires first the calculation of the autocorrelation function. From this, then the energy spectral density is obtained by taking the Fourier transform. However, in practice, we mostly deal with random signals which are short segments of infinite length signals. These are typically power signals, and although some signals can have periodicity patterns, they are also in general aperiodic. An example of power signal is the unit step function, which is 1 for positive times and 0 for negative times. The energy of such signal is given by the integral of 1 from 0 to infinity. In fact, the modulus squared of the signal is equal to the signal itself. Obviously, this integral is infinite. Thus, we can conclude that the unit step function is not an energy signal. To calculate the average power, we need to take the same integral over an arbitrary period t, and then take the limit for t that goes to infinity. Let us see first what happens when we calculate the argument of the limit when t equals 1. In this case, we need to integrate from 0 to 1 over 2, and then divide by 1, obtaining 1 over 2. If we repeat the calculation for t equals 2, we need to integrate from 0 to 1 and divide by 2, obtaining again 1 over 2. We can thus demonstrate by induction that the power of the unit step function is equal to 1 over 2. Since the energy is infinite but the average power is finite, the unit step function is a power signal. In the following, we are using an equivalent definition of power for which summation goes from 0 to n-1 rather than from -n to n. Although in principle the FTD exists only for energy signals, we can define an approximate FTD that is the Fourier transform calculated on n samples, as given in the slide. Then, with the same reasoning as for the energy spectral density, we obtain the direct method to calculate the power spectral density as the modulus squared of the Fourier transform, where this time we use only n samples to calculate the FTD, and we need to normalize by 1 over n. And again, very similarly, we can obtain the indirect method to calculate the power spectral density as the Fourier transform of the autocorrelation function. In this case, however, we'll use an estimate of the autocorrelation function calculated on a limited set of time lags. If you are interested in the full proof, you are welcome to check out the reader. To summarize, most stochastic signals are periodic power signals, of which we have only a segment of n samples available. Since the observed signal is windowed, we can only look for an estimate of the power spectral density given the data. By the direct method, this estimate is obtained by taking the Fourier transform of the observed signal, calculated on n samples, and then taking the modulus squared. An equivalent way, referred to as indirect method, is to first calculate the autocorrelation function and then take its Fourier transform. The direct and indirect method are also known as periodogram and correlogram respectively. This concludes the screencast in which we discussed energy and power signals, and we introduced the periodogram and correlogram as the direct and indirect methods to estimate the power spectral density. Thank you for listening.